And in this final video, what we're going to do is look at calculating equilibrium constant, but this time not from the amounts at equilibrium, which is a little bit easier, but from the amounts at the start. Now we're going to need to know a little bit more information, but we're looking at how much we mix together. Maybe we've got the measurement of one of these things at equilibrium, and we're going to work out how we can find the value of Kc. So we've got an example here. I'm just going to scroll to the example. We've got 1 mole of ethanoic acid mixed with half a mole of ethanol and left in a stoppered flask of volume 1 decimetre cubed. All that information is going to be important, as is the amount at equilibrium. So we've got at equilibrium, the mixture was found to have 0.58 moles of ethanoic acid. But at the start, there was 1 mole of ethanoic acid and half a mole of ethanol and a volume of 1. All of this is important information. Now there's a little mnemonic, a little way to help you remember how to do this, and it goes RICE. We're going to have the ratio from the balanced equation. That is literally the numbers in the balanced equation. Now in this equation is all 1 to 1, so it's a nice straightforward example. There's 1 mole of everything. Then we're going to put in the initial amounts that we used. We used 1 mole of ethanoic acid and a half a mole of ethanol. At the beginning we had no products, we just mixed reactants, and so there was no products. Then we're going to put in the one thing we've been told about equilibrium, which is that there's 0.58 moles of ethanoic acid at equilibrium. What we do then is we look at how much the ethanoic acid has changed by, and the ethanoic acid has gone down by 0.42. It's the only change we can figure out. What we say to ourselves then is that whatever happens as a change must be in the same ratio as the balanced equation. So if I use up 0.42 moles of ethanoic acid, according to reacting quantities, I must use up 0.42 moles of ethanol as well. So these two lines, our ratio line and our change line, must be in the same ratio quantities. So where 1 to 1 to 1 to 1 must be 0.42 to 0.42 to 0.42. Each of those numbers is the same. Remember, reactants go down and products increase. So we're going to put a minus on the reactant side and a plus on the product side. We're going to apply that to the initial amount to find the equilibrium amount. So we end up with 0.08 here, 0.42 here, and 0.42 here. We've now got the equilibrium moles. But remembering that Kc uses concentration, so we're going to find the concentration, and just remember that concentration is moles over volume, where volume is in decimeters cubed. So we just go back and check our volume was nicely 1. So when we divide anything by the number 1, we are just going to get the number itself. So we've got 0.58, 0.08, 0.42, 0.42. And we're going to put those into our Kc expression. So have a go at writing your Kc expression for this reaction. So if we do that, we should see that we've got those products over the reactants. We've got no units because there's equal numbers, so we just put our numbers in and calculate it. 0.42 times 0.42 over 0.58 times 0.08, and we calculate that. I'm going to give it to two significant figures, 3.8. Well, in fact, I think we should really give it to 3 significant figures, shouldn't we? So let's just check what it is. So 0.42 times 0.42 on your calculator, and it's coming out to be 3.80. No units. Let's have another go at that RICE method. So having a look, H plus I2, and you can see it goes to 2I, so the ratio is 1 to 1 to 2. Remembering it's the ratio line and the change line that are going to be in the same relative proportions. We're going to put in our initial amounts, 1.00 moles of that and 1.00 moles of that, with no products. And at equilibrium, it's telling us that there's 1.60 moles of product made. So you can see that this has gone up by 1.6. Now remember that these two lines, ratio and change, are in the same proportion, so 1 to 1 to 2 is the same as something to 1.6. So if 1.6 represents 2, then 1 would be 0.8. And also remember that reactants go down and products go up. So we get 0.2, 0.2 and 1.6. Then remember that what we do to find concentration is divide by volume. And we haven't been given a volume. So why haven't we been given a volume? So just remember what we said in a previous video about your expression. So have a look at your expression again. We got HI squared over H2 I2. Now we can just put this volume as V for now. We don't know what it is, but we don't need to know what it is, because what are those units? So we can see that there's no units from this expression. So if we were to put our numbers in for Kc, we'd have 1.6 over V all squared, 0.2 over V, 0.2 over V, and we can see that all those V's are going to cancel out because we've got 2 V's on the top and 2 V's on the bottom. So Kc is 1.6 squared over 0.2 squared, 0.2 times 0.2. You can put that on your calculator and calculate the value for Kc. If you do that, you'll see that you should get 64 with no units. Okay, have a look at this one. See if you can work through the method. It's a little bit trickier on the unit, so pause the video now and see if you can figure out an answer yourself. So I've written my expression and worked out my units, and I'm just starting to put things in to my Rice method, and you can see I've put in all the data that was in the question and worked out that first change. And remembering that the change line and the ratio line are in the same proportion, so that's the one we're relying on. So if a 4 is equivalent to 0.6, then this would be equivalent to 0.15, because that is a quarter of 0.6. And a 2 would be 0.30, and remembering that our products go up. So we apply that to the beginning bit and we get 0.05, 0.30, 0.30, and then we're going to find concentration by doing moles over volume, and our volume this time is actually 10 decimeters cubed, so we've got to divide by 10. So we can do that. Each time, put the numbers in, calculate the value of Kc. So you put your numbers in, 0.03 squared times 0.03 squared over 0.02 to the power of 4 times 0.005, and type that on your calculator. If you do that, your calculator is going to say this, but remember that we're trying to give our answer to the appropriate number of significant figures, which in this case is 3. So 1012 becomes 1010 to 3 SF, and our units were moles to the -1 dm cubed. So here's another one. Pause the video and see if you can work it through. Remember that when 40% had dissociated, what that means is 40% had reacted. 40% of the initial is the change, 40% reaction, 60% left at equilibrium. So 60% at equilibrium, 40% reacted. So pause the video and have a go, come back and have a look at the answer. So if you've managed to do that, you should have got this answer. Just notice that 40% of 1 is 0.4, so the 0.4 has been lost, 0.6 remains at equilibrium. And if 0.4 has been lost, 0.8 of the NO2 has been created. I've divided through by volume to get concentration, and I've put those into my Kc expression and given the answer to 2SF. So we've got another one here. It's a little bit harder now. These are kind of extension for A level. You've got to find out the initial amount. So you've got the Kc, then you've got the amount at equilibrium. So let's put in what we've got. So let's just pay attention to the fact that we've been given the Kc, but we've also been given, calculate the number required to produce 1 mole of product, 1 mole of product. So that would be our equilibrium moles. Doesn't want me to stay on the page today. 1 mole of product there from 4 moles of propanone, and we've got the V here. Okay, so this is what we've got so far. I've just put that in the wrong box there. Let's put that in the right box, because what we should have put in here is our ratio 1 to 1 to 1. Now it says let X be the thing we're trying to find out, and we know that we start off with no product. Put an X in there. So we can see that we can find that first change, and we know that the change line has to be in the ratio of the balanced equation. So 1, 1, 1, but the reactants go down and the products go up. So this would become 3, and this would be X minus 1. Now we know that our volume is 2 decimeters cubed, so we're going to do 3 over 2, which is 1.5. We've got X minus 1 all over 2, and we can't do anything with that. And we've got 1 over 2, which is 0.5. So let's write an expression for Kc and try to substitute in what we've got. So I've just substituted in the numbers that I've got. Now I've got to do some rearranging. So I've put in the values that were in the table and the Kc. I'm going to multiply both sides up, okay, by the bottom line. So I'm going to do 30.0 times 1.5 times that bracket X minus 1 over 2, and it equals 0.5. Now I'm going to divide both sides by the 30 and the 1.5. So X minus 1 over 2 equals 0.5 divided by 30 times 1.5. Okay, so now I can multiply both sides by 2. So X minus 1 equals 2 times all of this, and I can type that on my calculator to work it out. So you can put that into your calculator and find that you can find a value for X minus 1. And what you're seeing is 0.0222 recurring, so X equals 1.02 when we give it to 3 significant figures. Now there's one final extension question there for you to have a go at, and maybe if you pause the video and come back and look, this is beyond the level at A level, but it is a good little challenge for those of you wanting to go a step further. So you might have got this far. Now what you don't need to do here is you don't need to multiply out those brackets and make a quadratic, because although in maths, if you had this expression, you would find that you've got a positive and a negative root. We won't have the negative root in chemistry, so what we can say is actually that this is the same as 1.5 squared over X minus 0.75 squared, and we can just square root both sides. If you square root 64, you get 8. And if you square root the right hand side, you just lose those square signs off both the top and the bottom. Okay, so then you can multiply both sides by X minus 0.75. And you can multiply out the bracket, 8x minus 6 equals 1.5. So 8x equals 7.5 if you add 6 to both sides. So x equals 0.9375. So that is a little bit of a trickier one, but it is beyond the spec, and we wouldn't expect you to be able to do it. It's a nice little challenge though.